right? We're going to do the basics of helicopter aerodynamics. Those of you who missed out the first session are going to get a quick recap in this session. Alright, so what we basically did in the last class, I'll summarize in a few short time, and then we'll proceed on to the next session. Right now, helicopter kind of looks like this. You have a main rotor and you have a tail rotor, right? This is your main rotor. This is your tail rotor, and this forms your fuselage. Alright, main rotor, and the main rotor forms a disc which is called as main rotor disc, or just rotor disc. So now, if you have a helicopter fuselage, tail rotor and main rotor, right? Now if I define some axis like this, and this axis and this axis, along negative of x is my forward flight, right? So now any rotation about x, y and z, this is roll, right? So now any rotation about z is pitch. A positive pitch is referred to as pitch up, a negative pitch is referred to as pitch down, and a rotation about y is yaw. Alright, so now you have roll axis, you have pitch axis as well as the yaw axis. Now most of the helicopter arrangements are like this. You have a main rotor in the front followed by a tail rotor at the back, right? You have a main rotor disc and a tail rotor at the back, and this is aligned to forward speed of the helicopter, which is VH. Let me call it VH, forward speed of the helicopter. VH, V of the helicopter, F for forward speed, right? Now this is the most commonly available configuration of the main rotor of the helicopter in respect to the rotor position, right? So now you also have another configuration, which is this. You have another main rotor. Alright, now you have another main rotor at the back. Now this type of arrangement is called as tandem arrangement. This type of arrangement is called tandem arrangement. Now you also have another type of arrangement wherein the rotors will either intermesh into each other. For example, if this is your top view of the helicopter, if this is your top view of the helicopter, now you have a rotor disc and you have another rotor disc here and here. These two rotors, or these two rotors, rotate such that the helicopter rotors will mesh into each other. For example, if the helicopter blades are placed like this, let me say, just like this, then these rotors will be like this. Alright, so they will never touch each other, but they will intermesh into each other. Right? These are called as syncropters. Again, the advantages with tandem arrangement and syncropters is that you don't need a tail rotor, because tail rotor is used to balance the torque produced by the main rotor, in which case the torque produced by the main rotor is cancelled off by the another secondary main rotor, so you don't have any net torque which needs to be balanced, so you don't have another tail rotor, right? So now coming to the arrangements of the helicopter rotor, we have an assembly called a swash plate assembly, which is placed in a rotor hub. The helicopter rotors in blades are in fact attached to the rotor hub through some kind of different types of assemblies. There are many different types of assemblies available. One is a simple swing arm type or the seesaw type, and you also have a complicated system like a completely articulated system or even an all composite hub, right? So now each one has its own advantages and disadvantages. For example, the all composite hub was developed extensively during the Black Hawk and and even Me helicopters. So now the advantage with that is it is simple to understand and it is simple to design. But the disadvantage is it is as simple as it is designed. It is as complicated also because it has a number of moving parts, and the assembly itself is is very complicated, right? So now there is in fact an example that ALH uses all composite helicopter rotor hub, now all composite helicopter rotor blades, and this has proved that it has reduced the total number of components something like from 3000 to under 1000, which is a huge advantage in terms of assembly and also in terms of design and simplicity, which is always beneficial, right? Now coming to the helicopter rotors themselves, you have a hub, you have a helicopter hub. So now this is the rotor shaft, this is the rotor shaft, and you have a hub, and your individual blades themselves are connected like this. Okay, and now these will rotate. Alright, so now as you can see, this as they rotate, this forms a circle. This is, you know, that it is a rotor disc, it is the main rotor disc. Now if you create an axis here where your tail rotor is there, alright, now about this axis, if I consider an angle here called phi, that is called as azimuth. This is called as an azimuth angle. So for example, if you have n blades and you want to determine the angular positions of each of the blades with respect to this axis, then the azimuth can be used very easily like this. Let's say that I have a few more blades here. Right? So now what I do is I write phi of the kth blade, and what I do is when I phi, I refer to the blade which is just past this axis. While it is rotating, it would have just passed the axis, this axis, main helicopter axis, front to rotor, tail rotor, and with respect to that blade alone, I define the value of phi, right? So I give that value phi. So since it is moving in a circular fashion, I can generalize the entire formula and then give a formula for any kth. For example, k equals 1, k equals 2, k equals 3, k equals 4. So if in this case what I can do is 2 pi over n multiplied by k minus 1, where n is the number of blades in your helicopter rotor. So you define your azimuth of each of the blade of the kth blade using the azimuth of the first blade plus 2 pi divided by the total number of blades multiplied by the kth blade minus 1. This is simple to understand. Okay, so now we'll come to a well-known problem which you already understood from the stall, that is wingtip vortices. In the same like wingtip vortices, you have rotor tip vortices. When it is rotating like this, what you are going to have is you have an airfoil. You have an airfoil. As it moves along, the air from the above feels that it is having a higher pressure, and it wants to move to a region of lower pressure. So what it does is it moves from the underside. It moves from the underside and then tries to come up. When it tries to come up, it creates a vortex. So what you have is you essentially have a vortex motion like this. Alright? You will have a vortex motion like this, and this vortex will be directed towards the inner direction, towards the rotor hub. Right? So now you have a rotor. These are called as rotor tip vortices. Or just rotor tip vortex. Okay, now that is not the only thing which we have here, alright? So now what theory of aerodynamics suggests is any lifting body gives rise to vortices. So this is also a place of a lifting body, not only here, right? So as it tries to go up, what it does is the entire you are going to have circulations everywhere. You're going to have circulations everywhere. So now combining all this, so what you will be having is you will have a helical screw type helical wake, which rotates and comes downward towards the fuselage and hits the ground. That is called as helicopter rotor wake. Alright. Now how do I draw the diagram for that? I'll remove this for the moment. So now if this is my helicopter, so what is happening? I have the wingtip vortices. These are rotor tip vortices. Okay, so now you also have another flow here occurring like this. Alright, this forms a sheet with the center. Right, so now this is a sheet, and this helical sheet moves down as you rotate. Alright, so now you have a helical, it's kind of like a helical paper which has been opened up. Right, so now you get these type of wakes. These are together called as just main rotor wake. Okay, so now you have, this is called as main rotor wake. This is very important, and this is a very decisive factor for the helicopter design, helicopter rotor design, and also the fuselage design. Okay, and greater the weight of the helicopter, greater the maximum takeoff weight of the helicopter, greater is the required thrust. Once greater is the required thrust, what you have is you have a high amount of lift which is required from each of the rotor blades. Once you have a very high amount of lift which is required, the vortex energy which is required is also goes up. Alright, once the vortex energy goes up and the wake vortex energy, wake energy goes up, this segment becomes more and more strong and strong in terms of its energy which is contained, and that is why bigger helicopters need once a bigger helicopter passes by, another for the there needs to be a large amount of time which is required for any other small aircraft to enter into that space, because all these vortices would still be revolving around the axis even though the helicopter has passed down. Right. So now we'll see what happens to these rotor vortices as the helicopter is moving. This is in terms of power. right? Hover is a flight condition where the helicopter stays stable above the ground without any relative motion with respect to the ground, alright? And the helicopter as a whole. So now we will consider forward flight or any other flight apart from hover. So now what we will do is we will consider the same helicopter, but the helicopter has a forward velocity v. Okay, it has a forward velocity v, and let it also it has a forward velocity v. So now this will get extended backwards. This is your hub. This is where the rotor will start, and so consequently you will have a helix like this, and also a helix like this, and this, and this, like this. So you will have a rotor wake which is extended backwards. Okay, so now each one of these dots, if I zoom it in, it is essentially a circulation. It is essentially a rotation or a vortex. Alright, now this vortex has a very complicated three-dimensional geometry, giving it shape here. It looks like this. Now if this is the axis of the rotor tip vortices, now I have the it is going to form a vortex helix. Alright, so now each one will rotate about its own axis like this. It will rotate, rotate. So this is a very complicated field. Greater the amount of lift which is needed, greater will be the vortex strength. And greater is the vortex strength, greater is also the time which is required for the vortex to die, or the vortex decay time will increase. Okay, so now we have understood the some aspects of helicopter rotor wakes. We will come to the actual assembly of this blade to this, and what other controls are there. Okay, so now I'm going to draw a simple helicopter rotor. Let this be my rotor disc, and this is my hub, and let me have my blades. If this is my blade, what I'm going to have is, I'm going to have an extension here, right? I'm going to have a small extension, and what I'm going to do is, I'm going to take a rod which can swivel along this place. Okay, now this rod can move up or down. Alright, this is basically a control rod. Okay, now what it helps is, it helps to change the angle or the pitch angle of the blade. Now every blade just like this, approximately. Okay, this is your blade. So now you have an axis. Okay, this axis is called as a feathering axis. Okay, the blade feathers about this axis. So now any angle with respect to this feathering axis gives rise to pitch up or pitch down of the individual blades. Right? If the blades turn up, it is either pitch up or pitch down. Okay. So now looking at this from another direction, this is your. If I take a section here, XX, section XX, right? So now let this be. I rotate the section, and if my airfoil looks something like this, okay. If this is my feathering axis, if that is my feathering axis, right? So now I make an attachment here, which is here, and there is a control rod which can move it up or down, and it has a bearing here. For blade, there's a bearing for blade pitch. So now what we do is we take the control rod here. Alright. So now what happens is if I push the control rod up, so it is going to take a shape like this, right? So effectively what you have done is you have increased the angle of attack of the blade. So you are pitching up the blade. So you have pitched up the blades by some angle, say alpha, right? Now that is the alpha increase. Now you can control the delta alpha by using delta y, right? So delta y, delta alpha is a function of delta y. Okay. So now you know that there is some mechanism which is available to control the pitch of individual blades. So now that you know that something like that is available, how is it made possible? Alright. Now this is made possible by using an assembly called as swash plate. Is made possible by using an assembly called as swash plate assembly. Okay, we'll see what it is and how it works. Basically, swash plate, what it does is it has a disc. It has a disc. Okay. So now below this it has another disc. But there are okay. So now this is number 1, this is number 2. So now what happens is this is connected below. This is your rotor axis. This is your main rotor axis. And what else do we have here? If I give this, you have the rotor hub. You have the rotor hub at the top, and you have the blades like this. And you have an arrangement for the control rods, which are attached to this top plate of this large plate assembly. Okay. So now you also have a similar blade. On this side, you have another control rod, okay, which can move up or down by delta y, delta y1, delta y2, and it can induce, delta y2 can induce a pitch change of delta alpha 2 and a pitch change of delta alpha 1. Okay, now this are the pitch changes introduced by these particular control rods. Okay, so now you might be wondering, this is a hollow disc. This has a central hole in its disc through which your this is your main rotor shaft. Right? This is your main rotor shaft. As the main rotor shaft rotates, but this is held stationary. This is held stationary. Okay, now as the main rotor shaft rotates, the rotor disc, the rotors are set into motion. Now, once the rotors are set into motion, the top plate and the rotors are connected by the control rods. Since they allow only they are locked in terms of rotational motion, relative rotational motion. So now, as this rotates, the top plate should also rotate because they are connected through the control rods. Alright, so the top plate will, if this is my rotor direction, okay, so now the top plate essentially will rotate like this. Okay, so now if this is my main axis, of the helicopter, I have the tail here. This is my rotor assembly, right? So now I'm blowing things out of proportion here. Please connect the dots, right? So now I have my helicopter here, just to give you a perspective of what is going on. I have a helicopter here, and this rotor part I have zoomed it up and I am showing it to you. Okay. So now here what I do is, suppose I want to fly forward. Okay. What I do is let's say take going vertical up or vertical down. Okay. Now you all know that you are familiar with this curve, which is basically alpha with respect to CL. It's somewhat like this. Okay. So now as alpha starts to increase up to this point, CL will also start to increase. So that you know that during vertical climb, you need higher and higher lift in order to achieve vertical climb. So what you need to do is you need to change the blade angles, blade pitch angles. Each of the blades needs to rotate about its feathering axis by a certain alpha to achieve the required CL. So how that is done is you move both the control rods simultaneously by the same amount. Okay, by move both the control rods simultaneously by the same amount. So in vertical climb, delta y1 is equal to delta y2, and also in vertical descent you have delta y1 is equal to delta y2. Right? So how that is done is, this entire bottom plate is pushed up. When entire bottom plate is pushed up, delta y1 should be equal to delta y2 because both are being pushed up simultaneously. So when delta y1 is equal to delta y2, delta alpha 1 will be equal to delta alpha 2. When delta alpha 1 is equal to delta alpha 2 is equal to delta alpha, for the same delta alpha, you will achieve the same delta CL in both the rotators, in both the helicopter rotor, in both the rotor plates. So that way you achieve a uniform increase in the lift on both the sides of the rotor. Okay. So now this will achieve vertical climb. In the same way, if you want to vertical descent, what you do is you lower the swash plate assembly. You lower the swash plate assembly, and one more thing, as this top plate rotates, this is a bearing. Okay, so this top plate is separated from the bottom plate by a bearing. So as the top plate rotates, the bottom plate will not rotate because there is a bearing in between. Right? So now this bottom plate is held stationary, and there is some assembly here through which you can change the motion of this swash plate. What assembly is that is, you have a rod here, you have another rod here, you have another rod at the front, you also have another rod at the back. Okay. So now if all the rods are pushed up by some mechanism from the bottom side, the bottom plate will move up, the top plate will move up, both the control rods will move up, the pitch gets changed simultaneously in terms of vertical climb only, and vertical climb and vertical descent. Now in terms of forward flight, what happens is the CL here, or the total lift here, will be greater than here. So you need to pitch up momentarily. So you will pitch up. So what it happens is, you will when the CL is greater, when the total lift is greater, whenever the rotors come towards the rear or come towards the azimuth of phi equals 0, then the lift will be maximum. When they come to a location where phi is 180 degrees, what I mean is, you have rotators. Now this is your main axis. So now phi is defined with respect to like this. When phi is 0, you have maximum lift in the direction of rotation. Okay. So now you have the direction of rotation is this. You have the direction of rotation occurring like this, right? Now phi is defined with respect to this. When phi is 0, you should have maximum lift because you want to pitch down. Once you pitch down, what happens is, suppose if this is your horizontal axis, okay, when this is your horizontal axis and this is your helicopter. Now once the lift on this side of this rotors increases, okay, so this is going to produce a moment. Alright, this is going to produce a moment because of which the helicopter will assume a position like this. Alright, so now you have a net thrust in this direction. Once you have a net thrust like that, this will give you a forward thrust forward, and thrust upward. Thrust upward keeps it in air, thrust forward takes it forward. Right? Not only that, there is this is an oversimplified version which I am showing you. In fact, the blades are going to turn like this. Right? Blades are going to turn, or they're going to deflect like that, because if you look at the helicopter rotor assembly, you are going to have hinges here. One, you have a flap hinge in order to allow the blades to flap, and the hinge which allows the blade to yaw. Okay, those hinges are necessary from the vibration point of view and from the structures point of view, and they interfere in the aerodynamics point of view. Now you have to consider also that, right? So when you consider that, what happens, because there are hinges, now there is a rotor hub. This is your hub. For this, your phi is less than 90 degrees. For this, phi is greater than 90 degrees, but it is less than 180 degrees, and for this it is greater than 0 degrees. Okay, phi is greater than 0, phi is between 180 degrees and 90 degrees. So now you have forward motion. So now if you want to turn backward, what you need to do? You need to control the control rods such that the lift at the front side starts to increase. That is, the lift for this type of rotor, for this rotor blade will increase, but that I can either decrease it or stay at the same. Alright, now what we do is, if you look at the slash plate assembly, if you give controls here, if this is my A, B, C and D, okay, now if I give equal controls to all, if A equals B equals C equals D, you either climb up or climb down. Climb up or climb down, right? Now this is achieved by the control called as collective. This is achieved by a control called as collective. Now there is another motion which you require. Okay, not only in the vertical axis, you also require motion along all the other axes. So how do we achieve that? Now you remember yaw. Yaw is basically the rotation about the vertical axis is yaw. How do we achieve vertical axis yaw? Just very simple, change the thrust produced by the tail rotors. So what happens? The thrust produced by the main rotors and the thrust produced by the tail rotors will not be same. So there is a torque imbalance. So that results in a torque imbalance. Because of the torque imbalance, you have a net moment produced about CG of the helicopter on the vertical axis. So that will give rise to a yaw. Okay, looking from the vertical direction, what you have is, you have a main rotor disc and you have a tail rotor disc and you have a tail rotor, right? So now in this case, what happens is, now there is a torque being produced because the helicopter rotor are moving. So now let's say that is the torque, and what do it tries to rotate the helicopter like that. So what you do, you put a anti-torque. Right, now this will produce a negative moment by which the helicopter will stay stable and will stay level about the x-axis. So now what if you want to change the yaw? Right, now this motion is called as yaw about this axis. This motion is called yaw. So now how do you change this? Just change the thrust produced by the tail rotors. How do we achieve that? It is simple. The same assembly is there in a similar assembly is there in the tail rotor assembly also, but the concept, one thing which differentiates the assembly with respect to rotor disc, main rotor disc and the tail rotors is that the tail rotors have only the collective. Okay, have only collective. That means the tail rotor blades can only simultaneously increase or decrease in their pitches or pitch angles. Alright, our angle of attacks cannot change much. Okay, now there is a lot of difference between angle of attack of a rotor blade and the pitch of the rotor blade, which we will which we will concentrate on it on the next session. So for this session, the tail rotors have only collective. Right, that's very important to remember. Tail rotor have only collective. They don't have any other controls. So now main rotor has collective and another control called as cyclic. It has another control called as cyclic. Now let's concentrate on what a cyclic is. Okay, what happens in a cyclic is, now we learned that A equals B equals C equals D gives rise to collective, right? What happens when A, B, C and D are not equal, right? Let us say that I want to tilt this strash plate like this. I want to tilt the strash plate like this. So what should I give? A is positive upwards. That's the plane, positive motion, negative motion, right? So now A is positive, yeah, and C will be negative because C is opposite to A. Bring that down, or you can do is bring A down and move A up, move C up. Alright, in which case, and let's keep B equals D. Okay, now if I keep this set of controls, what it does is when A is positive, let's consider A positive and C negative. So when C comes down,